Okay, we're going to wrap up our study of thermodynamics by looking at refrigeration and heat pumps. And we're going to start by looking at the Clausius statement, which is really just a restatement of the second law of thermodynamics. And it says that heat does not flow spontaneously from a cold to a hot object. And this should make sense. The way that heat works, of course, is because you have something at high temperature, meaning the particles are moving very rapidly, and something at lower temperature, meaning that they're not moving as rapidly. So you wouldn't expect spontaneously for the faster moving particles to become faster when they collide with the slower moving particles. Or for the slower moving particles to then move even slower after getting hit by a fast moving particle. These things don't quite make sense. So the implication is that in order to remove heat from an area of low temperature and transfer it to a high temperature area, we must do work. And water actually works as a really great analogy for these processes that we're about to undergo. If you have water at a high location, then it wants to fall. And what you do is you put something in its way, and as it's falling, then it does work for you. You can get work out of it. And we do the same thing basically with heat. You heat something up so it's at a high temperature, and that high temperature substance then wants to get to a lower temperature area. But you put something in the way, like a piston. And so now this high temperature region has to push into the low temperature region. And you get work out as a result. But just like with water, if you want to raise it up, if you have something at a low altitude, water at a low altitude, and you want to make it go higher, then you have to do work. And the same thing is true with temperature. If you have something at a low temperature region and you want it to go, and you want heat to travel from the low temperature region to the high temperature region, you have to do work. And so the bottom line here is that refrigeration requires energy. Now what we're going to do is we're going to look at a basic case of refrigeration. And this would basically be the inside of your refrigerator, if you're talking about a refrigerator. Or if you're talking about an air conditioner, this would be the inside of your house. And everything outside would be basically outside. Outside the refrigerator, outside your house, particularly these areas, most importantly, these areas right here. We're going to start our journey through the refrigerator right at this point. And right at this point, you have a really cold fluid. In terms of refrigerant, it's normally ammonia. And it may be a liquid right here, but it's probably going to be turning into a gas very, very soon, because this thing right here is called the expansion valve. We'll talk about that a little bit more later. But you basically have this really cold substance, and if it's not already a gas, it's going to be a gas very soon. And it goes through your refrigerator, usually starting with the freezer and then through a refrigerator. And what it does is, because it's so cold, it's colder than your freezer, it's colder than the refrigerator, heat is transferred from the inside of your refrigerator to the coils. And this works pretty effectively as far as keeping the inside of your refrigerator nice and cold, up to the point where this is now the same temperature because it's been heated up. It's now the same temperature that you want your freezer to be. At that point, it isn't effective at cooling it down anymore. Nor is it effective at keeping it from warming up, because eventually the outside temperature will want to even out with the inside temperature of your refrigerator and freezer. So you have to do something to keep the temperature from rising. And so what we do is we route it through this thing called a compressor. And what the compressor does is it takes this gas, this very low pressure gas, low temperature gas, and it compresses it. And you can basically think of it as just pushing something. It's pushing it. And what we know from our study of heat engines is that when we push things, when we push gas, we're going to do work on it. We're going to cause it to heat up. So we start off with this low temperature, low pressure gas, and we now have this high temperature gas, taking up less space, true, but at a very high temperature and at a very high pressure. What then happens is it runs along the back of your refrigerator or the bottom of your refrigerator, and because it's at such a high temperature now, it actually allows heat to leave it and transfer to the lower temperature environment of the room that you're in. So what ends up happening is, as it continues to go along, it cools down and it condenses into a fluid again, into a liquid, I should say. And so you now have this not really cool, but room temperature or maybe a little bit more fluid that has turned into a liquid from being a gas. Now it's still under a very high pressure. This is blocked off here. This is blocked off here. For the most part, blocked off here. And so you have this really high pressure, moderately high temperature liquid. And it gets to a metering device, or sometimes known as an expansion valve. And when it passes through here, all of a sudden, everything opens up for the little bit that's allowed through at any given point in time. And you go from this high pressure to this low pressure region, and it's allowed to expand. And you can imagine that this is very similar to when you blow air out of your mouth. If you have your lips very tightly pressed together so that there's only a very small opening and you blow through it, put your hand in front of that, you'll notice that the air temperature seems pretty cool. Well, this is very strange because the air is coming from your lungs, which is inside of you, and you should be 90-some degrees. You'll get the more sort of direct from lung effect if you keep your lips wide open and blow out. And just breathe out that way. And you'll notice that the air temperature is much warmer in that case. So you can go from having a pretty warm fluid to having a very cool fluid just by making the opening narrow and forcing it to expand. And that's where we kind of started with. We started with this expansion. It started off perhaps as a liquid, a very cold liquid, and then as it continued to expand, it became a gas into this low pressure region, low temperature, low pressure. It's at a lower temperature than the insides of the refrigerator, so it takes in heat, and so on, and so on, and so on. I'm going to show you just another brief example, and then we'll go a little bit deeper into the process and into some equations. So this just picture isn't really any different from the picture I had shown you previously, only it actually labels things for us here. So we'll start off here at the end of the metering device, they call it, same as the expansion valve. And you have this low temperature, low pressure liquid, probably turning into a gas pretty quickly. And it goes through what's called the evaporator, which is basically the inside of your refrigerator, freezer. And it takes relatively hot air out of the inside of your refrigerator and freezer and puts it into the evaporator. Sometimes, depending on what you're doing, you actually will blow air over the cold pipes of the evaporator to better circulate the air into the refrigerator or freezer. And then you still have this pretty cool, it's low temperature, still low pressure, but it's warmer, and it's now a vapor. And it goes through the compressor, and the compressor causes it to be at a very high pressure, very high temperature, still a vapor. And then as it cycles through the back of your refrigerator, at the bottom of your refrigerator, normally what happens is air gets blown over those coils to facilitate the exit of the hot air, or the the very high temperature of the coils. It facilitates transfer of heat from the very hot vapor inside of the coils to the cooler air outside in the room that the refrigerator's in. And that means that we end up getting not a gas anymore, but a fluid, a liquid rather, inside of those pipes. And then they start the process all over again. Now, just to make sure that this process is very clear, I'm going to draw some heat diagrams just to show what's going on. And so what we have going on here is you have heat. Oops, that's not what I intended to do. You have heat at a low temperature, from a low temperature area. So this is your low temperature region. Your low temperature aspect is inside of here. And you have heat flowing into that low temperature region from a pretty low temperature area. And then it goes through the compressor, gets really hot, and now you're going to have heat leaving. And so this is your high temperature area, and it's going to leave, heat is going to leave that high temperature region. And that's really the basics of what's going on. Now what we're going to do is get into some equations, and we'll refer back to this picture to make sure that everything's nice and clear. So these are your basic way that you measure refrigerator efficiency. We don't do it the same way that we do engine efficiency. We use something called the coefficient of performance. And it measures how effective it is. And the higher the number, the better. This isn't like efficiency. It's not capped at 100%. It's not a percent at all. It's just a number. So for coefficient of performance for a refrigerator, the actual coefficient of performance is determined by how much heat you remove from the inside of your refrigerator compared to how much work you had to do to get that much heat removed. Now, ideally, this isn't going to be a low number at all. This should be a pretty high number, like 10 or 12 or something like that, because you should be able to, with a little bit of work, remove a lot of heat. An alternative way of stating this would be to say that, yes, the work is really just the difference between how much heat was put out compared to how much heat was taken in to the coils. And we can restate that then as an ideal case where you have this low temperature instead of QL and you have high temperature instead of QH. And so we see kind of an ideal bound for our refrigeration system. And I'll just go through and explain that briefly here. So TL is at best the temperature of the inside of the refrigerator. And what I mean by at best is that by the time your refrigerant leaves the refrigerator area and goes into the compressor, which is this guy right here, okay, so at this point right here, you want the refrigerant to be at the same temperature as the inside of the refrigerator. If it's if it's lower temperature than that, then you need to do more work during the compression process to raise the temperature enough. If the temperature of the coolant is higher than the temperature inside the refrigerator, then your coolant was actually heating up the inside of the refrigerator, which is not very good. That TH is, at best, the temperature of the room outside of the refrigerator. And the same types of rules apply. If your compressor wasn't able to heat it up enough, then no energy will be able to leave. So you won't dissipate heat, and the coolant will then be warmer inside of the refrigerator than it should be. If the temperature of those coils, and once again I'm talking about it right when it leaves this sort of heat giving off stage, so right around here, if it's not at the same temperature of the room, if it's warmer than the temperature of the room, then that means that you're not being quite as effective. Too much work was basically done on it, and so it's not going to be as effective cooling it down. And even if it is effective at cooling it down, it won't be as effective. You basically did too much work. And I'm going to show you a little bit more with this, with some pictures and some numbers. All right, let's say that the outside temperature of your house or apartment is about, let's go with 295 Kelvin. And the temperature you want the inside of your fridge to be is 275 Kelvin. So just over the freezing point of water. And so this will give us our ideal, and we can look in and find out what is the coefficient of performance for this. And that's just going to be TL divided by TH minus TL. And it's important to do it in Kelvin because we're not dealing with just differences in temperature. We actually have a real temperature here that we want to work with. So you would have 275 divided by, in this case, 20. And you'll see that the coefficient of performance will be pretty high. It'll be a little bit over 10. This is the ideal coefficient of performance. This is the best that we can do. If we don't overshoot it all, if everything goes according to plan, and if we ignore friction. Okay? This never happens. You'll never get the coefficient, the ideal coefficient of performance. So what we can also look at is what is the actual coefficient of performance. And there's a number of different ways that we can do that. We can say, well, let's take a look at how much work is done. Let's say that we're doing 100 joules of work when this is running, and for that, we get out, let's say, 700 joules. So this is our goal, and this is what we had to do to get to our goal. And so the coefficient of performance would be QL divided by the work. And so you would get 700 divided by 100, or an actual coefficient of performance of 7. So much less than this, but still not too bad. The next lecture, I'm just going to finish this up with refrigeration, do a couple of things with coefficient of performance and ideal coefficient of performance, and then we'll do some heat engines, and we'll be done.